All right. In this lecture, we will talk about regularization techniques for logistic regression. This is not in the book, and there are regularization techniques in the book, but not for logistic regression. So for logistic regression, I have created these lecture notes. So if you remember, for logistic regression, the conditional probability of response given features was this linear function that goes through the sigmoid. And then the probability of data given, beta and beta 0, is the multiplication of the probabilities for each data point, because each data point is independent of the other one. So we separate the ones for which the label is 1 from the ones for which the label is 0. And for those which the label is 1, this is going to be the conditional probability, and for those that where the label is 0, this is going to be the conditional probability. And then you can simplify this mathematically to e to the power of the summation of yi times xi transpose beta plus beta 0 divided by the multiplication from I1 to n of 1 plus e to the power of xi transpose beta plus beta 0. If we take the log of this to get the log likelihood, the log likelihood is the log conditional probability of the data given the parameters. So the log probability of the data given the parameters is going to be the sum of yi multiplied by xi transpose beta plus beta 0 minus the sum I1 to n the log of 1 plus e to the power of xi transpose beta plus beta 0. And then the negative of it will be the negative, so we want to maximize the log probability or minimize the log likelihood. Maximize the log likelihood is equivalent to minimizing the log likelihood. So the negative log likelihood here is our cost function. Okay. So the measure of error here is 1 over n divided by the negative log likelihood. This is the negative log likelihood. So the same way that the measure of error for linear regression is the mean squared error, here we have this term, which is equivalent to the mean squared error, but for logistic regression, obviously the equation is going to be different. What matters is that this loss function L depends on beta, the coefficient vector, and the intercept, beta 0. Now, small negative log likelihood of beta and beta 0 means the logistic model with parameters of beta and beta 0 is a good fit to the data. Now, um, if we just simply find, so what I will do here from now on is I will ignore the dependence on beta 0. I will absorb it into beta. That is possible by adding one extra column to X with all ones. So for simplicity of notation, I will just use beta. If we're talking about the maximum likelihood estimate, we seek the beta that minimizes this loss function. But people have learned over the years that sometimes it's better to not only try to find the beta that gives us the best fit, but also a beta that, in addition to giving a reasonable fit, has a small L2 norm or a small L1 norm. L1 norm is the sum of the absolute values of beta. L2 norm is the sum of squares of the elements of beta. And there are two big important examples in this avenue. One is called ridge regression, the other one is called lasso, and the book introduces these in the context of a linear regression. So our focus is not linear regression or regression in general in this video lecture, and therefore I will use the general form of the loss, which for logistic regression is this term, which is the negative log likelihood, and for linear regression is the mean squared error. But regardless of what model we talk about, this is a loss. This is a measure of how well the model fits the data. And this term is a measure of how complex the model is. So for many reasons, the L2 norm of the vector of parameters can be a surrogate for the complexity of the model. Because if the L2 norm is large, that means that the range of values that we are allowing beta to take is large. So we allow a larger class of models to fit the data. But if the L2 norm becomes smaller, that means that the elements of beta are limited, and when they are limited, then the range of values they can take is also smaller, and therefore the um, the space of possible models becomes also more limited. Now you may say, what is lambda here? Lambda is a non-negative number. It is a tuning parameter. It essentially balances how much we care about fitness versus model complexity. So this is fitness, model complexity. So we want to have a trade-off between the two. There is a trade-off, obviously, and we want something that is not too complex, but also doesn't lead also to a big loss. Okay. Now, Elastic net is a combination of ridge and lasso. It's a combination between the L2 norm and the L1 norm. So an extra free parameter as alpha is introduced. Alpha is supposed to be between 0 and 1. If it's 0, then this term is 0 and we will end up with ridge. If it's 1, this term is 0 and we will end up with lasso. And in between, we have the best of two worlds. What is the best of two worlds? Well, what are the two worlds? Ridge is a world where the coefficients are shrunken. Lasso gives us a beta hat that is sparse, meaning that coefficients that are not strongly associated with the response, instead of having a very small value, will be clamped to 0. This leads to simplicity because in many scenarios we have many features and we know that a small subset of these features are associated with the response, but we do not know which subset. And since there are many subsets, it's a complicated, complex exponential space that we need to search if we wanted to find the best sparsity pattern. But lasso, by nature, by virtue of the absolute value involved in the L1 norm, clamps coefficients that are not associated or are not strongly associated with the response to 0, and the rest will be shrunken a bit. Whereas ridge will never clamp the coefficients to 0. It reduces them, it shrinks them, but it will always be a small non-zero number. So for the sake of parsimony, lasso is preferred, but the ridge is faster, slightly, and easier to solve. There is another thing which is very important. If we have collinearity, meaning that there are features that are strongly correlated and they are associated with response, what lasso will do is it will clamp all of them except 1 to 0. So if we have three covariates which are strongly correlated, they are strongly dependent, so there is a group of variables that should be together present or not present, what lasso will do is it will clamp all of them to 0 and pick one of them, and which one is pretty arbitrarily to some extent. That is not desirable, because if we have three features which are strongly correlated, then essentially either all of them should be in or all of them should be out. Now the good thing about elastic net is that it clamps the coefficients that are not associated with the response to 0, but it will also have a grouping effect, meaning that if there is a group of features that are strongly associated with the response, it will select them, whereas lasso would have clamped most of them to 0 and keep only one. What is this figure trying to tell us? Well, we have P features. P features, each of them can be present or not present, so we have two options, yes and no. And then if you want to count the total number of possibilities that we can have, is 2 times 2 times, so it's essentially 2 to the power of p, exponentially large number of models we have here. and um, yeah, too complex to search for the whole space. That's why we used something like lasso, because it just solves an optimization problem instead of searching over an exponentially large family of models. Okay, so lambda here is a tuning parameter, and if lambda is small, then we essentially end up with a scenario where um, we are just solving the MLE, right? So lambda small gives us a complex model, lambda large gives us a simple model. So I say it again, lambda small gives us a complex model, because when lambda is small, the importance of this term becomes um, negligible, and the major contributor will be just the fitness. Therefore, we will find the model that fits the data well, and typically the most complex model fits the data better. The same applies to lasso. On the other hand, if lambda becomes large, the importance of these two terms becomes more prominent. And when that happens, then we want to try to find betas which don't have large L1 norm or L2 norm, and that will give us simpler models. Okay, so let's look at an example. Um, this data is, you can take it from this website. It's from a paper, Analysis of Hidden Units in a Layered Network Trained to Classify Sonar Targets. Was published in the Journal of Neural Networks. So let's look at this for a second. So this is the data set used by Gorman and Sejnowski in their study of the classification of sonar signals using a neural network. Okay. We want to discriminate between sonar signals bounced off a metal cylinder and those bounced off a roughly cylinder rock. So they have these metal cylinders apparently at the bottom of the ocean, but they don't know where they are. So they have these ships that just cruise the region, and they just bounce off these. They just send these signals, and the signals bounce the floor of the ocean, and they come back. And based on the power spectrum of the bounced back signal, we want to locate metal signals. So each pattern is a set of 60 numbers in the range 0 to 1. Each number represents the energy within a particular frequency band integrated over a certain period of time. And the labels associated with each record contains the letter R, standing for rock, and M for a metal cylinder. data frame, we have 208 observations, 61 variables. I also use this data in my paper, Journal of the Royal Statistical Society, and I show you. It's a very nice example. In the numerical experiments section, I give a summary, but you pass the simulation section and you get to the real data, the sonar data, and you look at page 7, figure 7, which is this figure, and I compare the performance of so here you see lambda,